Okay, welcome to my third live streaming experience. The topic is implementing deconstructors for Nim, and it's a complex topic with lots and lots of design questions that I'm trying to resolve here. In fact, there is a blog post about this already. You can find it here, and but it's work in progress. So I developed this document and the compiler at the same time, and when I figure out that things do not quite work, I work on the specification again. Okay, so what's it about? What I'm trying to do is zoom in, please, as usual. Okay. So yeah, we will learn about these rules. So keep them in mind already. So the point of destructors for Nim is to figure out like what kind of programs do actually need a garbage collector and which kind of programs do not. How can we make memory management more efficient or more deterministic, etc. So I'm starting with the idea that sequences and strings. I see. That sequences and strings are value-based in Nim, and so these are copied around already, and so the ownership for these is actually quite clear, and we can destroy a sequence when it goes out of scope, unless it escapes, right? And so we need a way to figure out when this escape can happen. But usually, let's assume things don't escape, and then we can clean up the sequence when its scope is left. And for strings, the same holds really. So maybe I'll show you some example. For example, if I have a while true loop and I am constructing a string with a concatenation, and then I output the string, and now some more Unicode would be nice so that I could have an arrow or something. Anyway, so here we can destroy the S, because there is no way this S could have escaped. So destructors need to be invoked when the scope ends, but also when we reassign a value. For example, say we overwrite this string with a new string, then this assignment here is actually, or needs to be implemented as destroy the old value of S, so free the memory, and then write the string into S. So assignments are destructive, and scope exits are destructive. And now the one other problem is, of course, to optimize these copies away. So for example here, well, that's probably not a good example, but in this case here we know the concatenation produces a new string for us, and we would like to move this new string into the S and not copy it, because that would just be a waste. And let's perhaps look at the rules again. So yeah, if it's a function application, we can actually move the result into the X. If it's not a function, if it's just some Y we don't know about, we need to copy it. And then here's a special rule, rule 3, which is I can also move this Z into X if I know that nobody else will ever read it again. It's actually just a special case of this function application here, because we know it produces a value that just vanquishes out of existence after this assignment. So that's why we can move it here, and this is the more general rule. The last read of the Z can be moved into the X. And the idea here is that I don't want to punish people for okay. I don't want to punish people for introducing helper variables, for example. Let's see if I have an X here, f of g. So we know g produces this temporary value that is only read once because it has no name. We can only read it once because it has no name. And but for readability, it might be useful to give it a name. I don't know, result of g. So clearly these are identical, and we should ensure that we can move this let variable into the f here. So in C++ it does something similar. So is the latest C++ standard actually specifies that copy elision has to be performed under some rules that are different from my rules, but I hope mine will work out better. Okay, let's see. Oh yeah, so we need to destroy values that have been constructed, but Nim doesn't really have a notion of construction in the language. So instead I say, okay, any function that returns a t, where t is a type that has a destructor, is actually a constructor of this t. And so for example, in this case, we need to introduce a temporary. We move it to the temporary. We call f with this temporary, and after the statement we need to free the memory again with this destroy here. So here the assumption is that that f only reads this temporary variable but doesn't take ownership of it. So since it doesn't take ownership, we need to ensure that the resources are actually freed by whatever g produces, and so we need this destroy temp statement here. Okay, so these are the 5 rules, and I've implemented them in the compiler. And now let's see if we can write a custom string class that doesn't use the garbage collector and yet produces no memory leaks. So perhaps let's look at the usage here. So since these are not the built-in strings, it's more tedious to work with, but hopefully we will be able to use this implementation as the new implementation that Nim's string will use under the hood. Okay, so I have a my string, or a variable of type my string, and then I create it to append here, and I create more strings, I concatenate them, and I convert them to something that Echo can handle. So this is actually dirty, but I need to avoid here that an allocation happens. And actually I fail because that allocates, but it doesn't really matter. It's just an example, right? And my string implementation is actually quite nice, so I like it. It's not as complex as C++ in my opinion, and it gets the job done. So we use Nim's memory allocator, dalloc here, and so this is not the GC, but just an allocator. And we count how often I call alloc and dalloc, and at the end these two numbers need to be the same, otherwise we freed things too often or not often enough. So maybe let's perhaps first ensure that we compile with the most recent compiler. So for those of you who do not know it, Koch boot is Nim's bootstrapping process. So, and the actually, so I want to, and the new destructors are hidden from ordinary users with this new runtime switch. Okay, so tests destructor t custom string, and yes, so we append some strings here, and eventually after this is all done, we perform 20 allocations and 20 deallocations, and that's pretty good. So let's look further into the implementation here. The destructor in Nim is called equals destroy, because it's a special built-in, so it's actually attached to the type. So these are also called type-bound procs. And so what do we need to do in the destructor? And probably I will get rid of this self here and make it more explicit to be able to show what's going on here. Okay, so we have actually a string consists of a length, a capacity, and a pointer to the data. And the length and the capacity do not really interest us, but we need to ensure to free the memory that's attached to this data field if it's not nil. And we set it to nil again, so that if you call destroy too often, nothing bad happens. And we set the length and the capacity to 0, so that everything is nicely cleaned up. I will now skip the sync part. I will explain this later. And this is the assignment. So assignment is, well, how to put it? It's actually tricky to get right, because you need to keep in mind two things. One is that, as I said, this is actually destructive, so it could be that A already has some data, and so we want to free that here. And the second thing to watch out is that it could be a self-assignment. So if I write x is equal to x, then it shouldn't free this data only to access it then in the read here. So we need to watch out that these are not identical. So now you might say, okay, but I mean, who writes code like this, right? So x is equal to x, yeah, that never happens. But at least in some sorting routines, it can occasionally happen that you, I don't know, access the same element without really noticing. So if I have, for instance, A at position I is equals to A at position J, then this is a self-assignment if these two indexes are the same. So we really should care about self-assignments. Okay, so we deallocate the data if we have some. Then we say, okay, the new length and the new capacity is taken from B, and we need to allocate the capacity, and the +1 here is for the terminating 0 for the C interoperability. And we need the copy mem. So this is one way of doing it. In older C++ standard library versions, it would actually do a copy on write instead. So I would have a reference count tracking how many users of this data actually exist, and only and so I would only increment a counter for this data here in this assignment and decrement it later. And I think I will show this in a couple of minutes because reference counting is obviously another important use case. But okay, as I said, we have value semantics here, so we are supposed to copy it, and we are allowed to not optimize this copy really. So let's perhaps look at these rules again. Yeah, that's not really interesting. Yeah, I will probably. Okay, so let's perhaps. So what is this sync doing here? And to explain sync, I need to actually show what the move would look like, and then explain why we don't use it. Okay, so assignment has to copy, but in some cases, as we have discussed, we can move things around instead. And so again, we need to watch out because A might already have data. So if it has, I need to free it. Actually, probably I will do it this way. So if it's the same, if it's a self move, then we don't do anything. If A had already something in it, we need to destroy it. And now the actual move is so A length becomes B length. The capacity is copied over, and the data is also just, so this is just a pointer copy, right? And now, since we move it, we need to ensure that B is actually empty afterwards. So we say, okay, B is now empty, and B has no data anymore because A took the ownership of this thing. Okay, so this is the move, and probably we will need this very soon. But now look at the signature here. Both are mutable, and they have to be mutable. Obviously I have to assign them to A, and I have to ensure that B cannot be read again afterwards. And so I need these three instructions here. But our rules say we move the call F to X, or perhaps a Z. Well, it's not clear what the Z here actually is, but actually in this case it's a local variable, but it could be a let variable. So this F call here has no address, right? So how can you mutate this one if it has no location, right? It has no location. And so the types signatures are mismatched. And so what I came up with was this sync instead. So sync is actually a move, but we know that this B here cannot be read again from ever again. And so we do not have to set these fields to 0. And so we can remove them, and we can turn B into a read-only view, and I think these are now pretty much identical. So if they're not really, because I merged these two cases into one, but so this is sync. And so the compiler doesn't use move, it uses sync. Because when it calls a move, it has proven that B won't be touched again afterwards. Okay. Okay. So these are custom strings. They work, and they are slower than Nim's current strings, unfortunately, but they do not use the garbage collector, and they are not really much slower. So probably we can optimize it more and get it to the same speed as Nim's built-in strings. Okay, so sequences. A sequence is pretty much the same, but this time it's generic. So we have a sequence of type T, and again we have length, capacity, and the data. And the destructor is more interesting, because now we have to destruct the data of this sequence. So the idea is that the elements in the my sequence are owned by this sequence, like in C++, the vector. And so if I free the sequence, I also need to free every element in there. And that should actually probably be x at x data at I, but since I have an accessor for this, it compiles. But we can do an optimization here, and this is the blinky hex chat is a bit annoying, yes. And sometimes we know that the data is simple and doesn't really have a destructor that does anything useful. And then we do not have to perform this loop over all the elements. And this is what this when supports copy mem does. So this is a built-in, so it's new. The compiler tells us if T is actually, if it has have a destructor attached to it, so a non-trivial destructor. And Dominic is saying, I wouldn't be able to concentrate with that blinking constantly. Yes, but actually I don't care, and these remarks in the chat are much more distracting than the blinking. Okay. So yes, this is just an optimization. I could remove this and yes, RX seems to have more trouble concentrating when we talk. Exactly. It's just an optimization and I could remove this line, but I don't want to. Okay, again we need to count how often we are calling alloc and dealloc. And so assignment, again we need to ensure that it's not a self-assignment. Again we need to see if A is has already some interesting things in that. And then we copy over this the elements in the my sequence. And here also we can perform an optimization. So if T supports copy mem, then we can copy the memory from B to A. Otherwise, we need to perform this copy manually and ensure here that the assignment is called, which might be overridden by a custom type T, right? And so this is again just an optimization. In general, if you see when it supports copy mem, it's just an optimization. Sync is exactly the same as for the string. Then I have implemented a resize here. So if the capacity is 0, then afterwards we set it to 8. Seems like a decent value. And afterwards, otherwise we multiply by 3 and divide by 2. So there's some paper that explains why this is a good formula. Okay, now more interesting things here. So this is add. Everybody knows sequences, the sequences add operation. And I also explained it in the blog post. The idea here is it's a template, and so the compiler can always see this line of code here, and this line of code here is an explicit assignment. And the idea here is that since the assignment is sometimes optimized into a move, we want to ensure that the compiler is able to do that. And so we ensure that the compiler can see this assignment here. And apart from that, it's pretty straightforward. So we reserve a new slot in the X, and this returns an unsafe address into this sequence that we can write into. So this is pointer dereferencing here. And I probably should stress again, so this is the implementation of a sequence. It's not that you are supposed to know how to implement sequences and strings in Nim. So after these experiments, if or when these become the built-in sequences and strings in Nim, they will look like you already know them. It's just that with these destructor features, you could implement your own custom containers that are as efficient as the built-in ones. So obviously this is unsafe code here, but it's the library implementation of what we are trying to do. So it's okay. I split the set length. Let's see it. I actually deprecated it because I think set length as it is in Nim now is actually misdesigned, because whenever I call set length, I know if it's a shrink or a grow, and so I split it up these two commands. So we have a grow that does some something with the capacity, and again copies the value into the data, and I need to give it an explicit value here. So, but for shrink, of course, I do not have this value. So that's why I think these should be two separate procs, in fact, because when you do currently, if you use set length for growing, you use the default value of t to grow it, but that's not always what you need, and so it makes sense to explicitly ask for the value that grow is going to take. Okay. So, and now I've made a constructor, but it's just a proc that returns this new my sequence of t. As I said, Nim doesn't really have constructors, and we don't need them. It works without it. Okay, let's perhaps look at how these can be used. So I create a sequence, a custom sequence with numbers from 1 to 6. Then I add the 89. Then I grow the sequence by 2 elements with the value 90, and then I output these values. And then I test that I do a create sequence here. So so 1 to 6, then the other numbers. And then I have this nested structure here, so I can also create a sequence of sequences, and I'm outputting the value to see if they actually contain what I wrote, what I've written. So 1, 2, 3, 4, 5, 6, 7. Okay. And again, we need to check that we haven't introduced any memory leaks or double frees. And this is okay. But it's also interesting. Why? Because it says you called alloc 6 times. And clearly I don't, because I create sequences called 4 times. So what's going on here? Why is it 6? Any opinions? Everybody is already sleeping. Why is it 6, not 4? Okay, nobody. Because of grow? No. In fact, I could disable this. Only the nested sequences is interesting. So it's still 5. Okay, I'll tell you why. If you look carefully into the create sequence, we are performing an assignment here, and we are performing an assignment for every element in this var args list, and the assignment also copies, and for the copy to work we allocate. that's bad. So these two are copied, and so that's not 3 creations but 5. And now the question is, how can we avoid this? So this assignment here is, so if we say we inline this a bit, so it's just pseudocode at this point here. So if the compiler would be able to see this, then let's look into the rules again. It's a function call, and x doesn't really matter, so it would be a move. So a suggestion is create a template, create sec. Yeah, perhaps. So as we've done for the add here, we want to be able to ensure that the compiler can see the assignment. So we could try and make create sec a template. And it's not the solution that I'm after really, but we can give it a try. Let's see. So well, even if I make it a template, then this is an implicit array construction here. And so what would be created is something like and so it wouldn't be, it would still be this elements at position I for which we have no rule to optimize against. So I mean, you could argue that's again this case 3 here, but we don't have an optimizer in the compiler that could detect that single array elements will never be read again. So that's out of the existing compiler technology. So what we could do instead is probably also eliminate this var args here. So okay, so Dominic is saying, sorry for the distraction, but Arak, in the future you should add your stream to the programming Twitch community. Yeah, I tried actually. I mean, I told Twitch that it's about programming, and Twitch didn't really understand the category programming and put me under I don't know, gaming or custom or miscangelous or something. But now that I know that there is actually a programming Twitch community, I could try again. Okay, maybe, so this is bad, but this array does not really have to be here. What if you use a macro instead? With a macro we can eliminate the array, and so maybe we should try that instead. And for this to work, I need to import the macros module. And I'm not so sure, because probably I want to keep this helper, but only do this step manually in the macro. So maybe this is raw create sec, take off, well, maybe it's just an overload, right? Could work. So no elements for this, but here we have the elements, and let's see. So what do I want to create? Actually, a list of statements. The first instruction is a new call bind some to create sec, and yeah, probably, I mean, I need to maybe, I don't really know if it will work out, but so that I can pass the type. I probably cannot really access this in this macro. Yes, I think it's just a bracket expression that we want to call, and the bracket expression is bind create sequence, and now I really don't know. Can I access the T in here? I've never done that before. Probably it would crash and smoke the compiler. So, and now I want to check. It's an interesting puzzle, really. Let's perhaps leave out the supports copyman optimization for first step. So I need to iterate. So for every element in elements, we want to add this thing here, right? So yeah, this is all wrong. This is all wrong, because I need to introduce some res. That I assign this create sec to. And now I can do Probably I could use quote do here, but I don't even have an I. No. Okay. This is also wrong because it needs to be a statement list expression, and the result of this expression is our temporary helper called res. So I'm probably I know this will fail, but let's see what the error message is. LMS is not declared. Oh yeah. So I want the length here. And this great sec. So people are highlighting me again. The channel says I don't know what the channel says. Some highly relevant stuff. So now I have this length, and this is all wrong. Let's see what the compiler complains about. Yes, okay, got node kind, in node type T. And how can I convert a type T into a nim node? I think maybe with get type. Is it even called get type? Okay, that works. Got nim node, but it's expected one. Oh, so nim node doesn't know about pairs. I could add that to nim node, so yeah, probably. It's, what's the plural of index in English? Indices. Come on, channel, be helpful. Indices. Okay. Yeah. cannot instantiate t. Well, at least the compiler doesn't crash, right? It's cool. It produces some error message telling me that create sequence cannot infer the type t or cannot instantiate it, stemming from this line. I could try and see if I can, maybe I can get it to work. I doubt it, but I bet it's really complex to make this work in the compiler. But so there's some other way to make the compiler output a stack trace for where this error message within the compiler actually occurs, but I can never remember it, so I'm using verbosity level 3 instead. Okay, so semi-ins generate instance. So it's a generic parameter, yes, and it's called from sem-resolved call. So we have a match, and we try to instantiate this generic proc in this case. So that's some resolved call, and in line 361 we have this bindings here. But bindings should in fact have a useful type for us. So let's see. You can use Control G to jump to lines in VS Code. Okay. Next time. So this is actually in fact here. So in this PT table, which is horribly named, there are the type bindings. And I think the problem here is, let's see, that I'm using get type of t here, and so so this is a new type instance that cannot be looked up into the type mappings that have been computed, but probably Yeah. And so that's why the compiler says I cannot instantiate this type t because get type made a copy of that. So we could try and fix this. So this is actually a generic parameter. So this is the get type implementation here. And what does it do for a generic parameter? It calls atomic type with a symbol. And does it work? No, sometimes. Too bad. Yeah. So this is calling atomic type X for reasons that I do not understand, but I'm not sure if I wrote this crap. Okay, but it doesn't copy the type. It's the same type. I don't want to lose too much time in this, but I will try here to perhaps add some debug output. So within the compiler there is an ID mechanism. And so that I can get reproducible results. So this is the idea of the type that we are interested in, and you can tell the compiler. So every type construction is done via new type, so we can enable this debugging output here, and this is actually a typo. And this is one of my favorite Nim features. We can write a stack trace everywhere if we are in debug mode. And so now that we know the offensive type, we will see where it is created. And actually it's created here in this some generic parameter list, which so it's processing a parameter list of generic types. Which is, let's see, too many open files. Eventually I'll find my file here. So when it processes this parameter list here, this one, and that's okay. So we know it's not caused by a wrong copy of some type, and so I don't know why it doesn't work. But as I said, I will look into this later. I don't want to spend too much time on this, because actually I wanted to do something entirely different. Okay, so let's assume this macro solution works. Then what's becoming annoying is nevertheless that you need to use templates and macros for every operation, just so that the compiler can see these assignments and perform the move optimization. So that doesn't really scale, in my opinion. So what we need to do is to have an explicit move, and as we can in fact, let's I think this one. What we also could try here is cheat and call the move operation explicitly. And yes. And let's see what happens if we do that. So now we have this 3 constructions. That's good, but we have 5 deallocations. That's very bad. We free things much too often. And so what we can say already is that the sync operation, so if the compiler invokes it for us, it's fine, but if we manually call it, it's wrong. And to see why that is, we could look at the rules again. So the offensive rule in this case is the rule 5, because the compiler is trying to help us in order to prevent memory leaks, and so it introduces a temporary variable that is then destroyed eventually afterwards. And this is wrong because in this case our f is create sequence, and it takes ownership of this TMP, and the destroy does harmful work. Now the problem is again actually hidden in this type here. So I take ownership of every element, but it's nothing like RT. So I cannot, so the temporary that is given to me cannot be marked as ownership has been lost. And so because I do not have the address of the temporary, but just the value of the temporary. And so this is why it cannot work. So one idea is what we could try is to write something like var t here. Of course, now this is a variable list of var t, so that's not a valid type either. But then I could again come back to my move, and the move empties the pointers in here, and the compiler would still produce this destructor call, which is not what we want, but it wouldn't harm us, because then the implementation of the destroy ensures that that it doesn't do anything really, because data is then nil, the ownership was taken, and the destroy does nothing. So, but even if this would work here, so this is probably not a valid type, but even if it were, I cannot call it in this way, because create sequence is not a location. I cannot mutate this. So one idea is to introduce a new parameter passing mode, which I called sync, which clearly marks t as mutable, but you cannot pass non-locations to it. So the result of a function call, you can pass the result of a function call directly to it. And apart from that, is actually the same as var. And this is now strikingly similar to what C++ does with its in C++ there's the distinction between a reference and a move reference. So this would be the move reference here, this sync. But it does make the language more complex. And so I don't really know which way to take. So if you have any ideas, please comment. Because so I also wrote it in the blog post, I think. With the C++ solution is the problem is that it bubbles up. So most of these operations in C++ now can take a move operator or a move location or a read-only location. So in C++ we have this pushback version 1, which would copy the element into the vector, or the version 2, which takes a movable location and moves it into the vector. And so in Nim we would have the same. So we would have a create sequence that takes a list of t's, and we would have a sequence that would take a list of these syncs, and we would need a way to disambiguate these two. So probably if I say create sequence like this, it would still call this version here that does the copy. And like in C++, I could imagine something like, oh no, move this guy and move this guy. And then it would resolve to this version. And it's not a good solution. Maybe we can do something else instead. So if we consider the rules again, what we could also do is to say we only have the move, so we only have this version, and if the element is used again afterwards, then the compiler produces a copy for us. So create sequence always takes ownership, but the compiler, since in this context, so here we are in a local context again where we can infer more things. So for example, I don't know, say we have this, and I don't know, maybe I add something afterwards, then the compiler could see, okay, so I can analyze this section of code, and I can see that this variable cannot escape into this call because it's afterwards still used, and so the compiler rewrites this for us as as a copy, and then we avoid this this split in the language where every operation needs to consider t or sync t, and I think that's actually comparable to what Rust is doing, because Rust defaults to move semantics really. So you move things around in Rust until you write a clone. But I don't think that's necessary, because we can infer if we need to introduce a copy to keep things safe. And also I think the Rust solution has a bad problem when it comes to code evolvability. So say the compiler required me to type in the clone explicitly, and then afterwards I changed my code, right? And so now the sequence is not read anymore afterwards, then I would still have these clone calls in there, but now they are not required anymore. And I think the Rust compiler wouldn't really complain and tell me that now the clone could become a move again. Whereas in the solution that I'm trying to come up with here, there is no such problem, because the compiler infers if it's a move or a copy, and it can, I don't have to change my code really just to please the compiler. So yeah, that seems like a decent solution. But if we say that sync t is actually what we need, then why do we need to write sync t? Why don't we leave it at that? And I don't know, change the rules. So this is actually a sync. So now we can use a move here. So now the rules change. So let's see. I will copy these. So we assume that F takes the ownership. So we do not have to ensure that the destructor is called at all. Instead, within the F, we probably need to inject these destroy calls, because there is a difference between must use the value once, or it may use the value once. To ensure that we don't get leaks, we actually are after the must here. But what is more convenient to use in practice is, of course, the may rule here. Or maybe not. I mean, it could also detect a bug. So say if I have a complex proc that creates a tree and I just forget to add the subtree into my final tree, then that's clearly a bug. And then this must rule here would catch this bug for me. But often in the compiler you have something like, I don't know, well, how to put it? Well, often in the compiler you have something like, I don't know, the ith child is either x or y. So I don't know. So let's say this is a tree construction thing here. And then you need to, or maybe let's do it properly. And then this may use rule here is what we want, because if the compiler says must use the value once, then okay, well, either I use x or y here, and so I would need to do something like, because I must consume, I would be forced to write this, and then I'm left with writing explicit destructors, and that's not a goal, because destructors need to be, or should be, injected into my code for me all the time, so that it's easier to use. Okay, so probably, and I think that's also going into Rust's domain, Probably within, so the new rules are this P takes ownership of these two. And so what the compiler needs to ensure that these two are really consumed all the time. And so I think it introduces, I don't know, X consumed, Y consumed, boolean. So the compiler injects these. And now let's rewrite it a bit. And that's like X is consumed, and else result is Y, and Y is consumed, and if not X consumed, destroy X, and if not Y consumed, destroy Y. And yeah, obviously these default to start with false. So that's also a pretty complex rule and a pretty complex code transformation going on here, but I think it would be doable. And then let's see again. So this rule 5 would become 5 tick, and the rule would be, I think, something like that. And I'm not sure if we are not shifting the problem around just too much, because now I got rid of these destroys here in this position, but I introduced them in the F. So I moved the destroys around. I don't think it really helps much, but as I said, the assumption is that it avoids bloating our APIs. So that we don't have to distinguish between T and sync T. However, if we introduce sync T and distinguish between T and sync T, I think the problem remains. So now the semantics are every element is consumed, and this is done in a loop, so it's tricky for the compiler to prove that really every element is moved. And so again, the compiler would inject the destructor calls for us in the body of this thing here. So I think there's no way to avoid this this code generation step here. Yeah, but I mean, yeah, it's tricky. It's tricky. Maybe we should make the macro solution work and say, okay, you need to write templates and macros to get these moves where they should be. maybe that's the solution that introduces the least amount of complexity, really, given the current Nim language. I don't know. So unfortunately, I didn't do much programming in this live programming session, but I mean, the topic was destructors, and the the specification is not really clear yet to me, and so I hoped it was interesting nevertheless, and I'm looking forward to the discussions that arise from this introduction into the problem domain. So see you the next time. Bye.